Of all the sciencey buzzwords to come out in recent years, this sounds like the one that is most likely to have been lifted from the latest Avengers script, but what does dark matter actually mean? The dark matter basically refers to the thing that should be generating the gravity, but we haven't the foggiest idea what it is. We don't even know if it's one single thing, and there's nothing to say that it should even be matter at all. It could be a force, a field, a force field, it could be something else entirely. We do know one thing about it though, it exists. We know this because we can observe its interactions with gravity, notably its lensing effect, which causes the light from other cosmic objects to bend with space-time. So what about dark energy? Basically, we can tell how quickly an object is moving away from us using something called redshift. Redshift is a type of Doppler effect, but with light. As an object moves away from us, the wavelength of the light that reaches us becomes stretched, and the redder it appears. This could well put it beyond red into infrared, but it's still light. Observing the redshift of distant galaxies is how we know that the universe is expanding. However, more recent discoveries have shown us that the expansion of the universe is accelerating faster than we think it should be, and so there must be something that we cannot observe or measure that is making it do that. This is what we call dark energy. Absolute zero basically refers to 0 degrees Kelvin, or 273.15 degrees C. It is at this temperature that all, or pretty much all, motion in an object ceases. Put simply, the uncertainty principle is a law in quantum mechanics that states that it is impossible to know both a particle's momentum and exact position at the same time. If you cooled a particle down to the point where its momentum was 0, you would know both, which is impossible. So you can't get right down to 0 K, but you can get close enough to produce some pretty amazing effects. Supercooled materials can become superconductors, meaning that they can conduct electrical currents without resistance. These superconductors can be used in everything from supercomputers to MRI scanners. Spacetime is a term that will crop up again and again in discussions about physics. This is largely due to the fact that, as a concept, it is pretty all-encompassing. The bringing together of space and time does away with the classical model of time as a fixed entity, independent of motion. It is now known that time passes relative to motion in physical space, and this is one of the basic principles of special relativity. Basically, you move through time in the same way that you move through space. For example, the Earth's orbit through space can be described as an ellipse, but its orbit through space-time is actually a helix. It is basically a branch of science that deals with the very, very small. It is a collection of principles and theories used to describe the behavior of matter and energy at the subatomic level. QM is concerned with quanta, discrete, indivisible units of energy. For example, light, which was always thought should be a wave of energy, can actually also behave as though it is made up of particles. We call these photons. In classic physics, it is impossible for something to be both a wave and a particle, but in quantum mechanics, it is perfectly fine. The thing is about quantum theory is that we can observe its effects, without knowing why a lot of them occur at the moment. It is a little bit like chemistry in the 18th century. We knew that certain things would happen when we poked around certain laws, but we just didn't fully understand the mechanisms behind it.